When a digital asset launches on a public blockchain, the environment is immediately hostile. Transactions first enter the mempool, a holding area for pending operations. Here, specialized adversarial actors known as searchers monitor the network for high-value trades. Because standard networks process transactions based on who pays the most to be first, this system rewards bots running Maximum Extractable Value, or MEV, strategies. They scan the mempool, copy the transactions of genuine participants, and pay a higher fee to ensure their trades are executed immediately beforehand. This dynamic triggers a gas war. Participants are forced into a blind auction, rapidly escalating priority fees just to secure block space. The result is a rigid bidding hierarchy where well-capitalized algorithms extract value, and standard users are priced out or forced to accept unfavorable execution. The underlying engineering flaw enabling this is sequential execution. Standard smart contracts process operations one by one, directly dictated by the order in which a miner or validator includes them in a block. Timing in this environment is highly manipulable. Any token distribution relying on transaction latency or single-point execution timing is structurally broken. The public mempool ensures that speed-based systems will always favor extraction over equitable access. The Secure Atomic Wave, or SAW protocol, decouples execution from speed, removing latency variables entirely. This grid illustrates the architecture of the protocol. SAW replaces chaotic event races with a rigid, cryptographically sealed state machine containing 12 distinct phases. The contract executes 12 phases in strict order. No state can be skipped, and no state can be rewound. To understand how this prevents network manipulation, we have to look past the symbols and examine the specific smart contract logic and cryptographic equations dictating these transitions. In adversarial environments, fair distribution requires deterministic mathematical boundaries. We begin with the structural anchors of the protocol: the foundation, genesis, and awakening states. State 1 enforces a strict lock. Token supply and contract bytecode process through a hashing function, generating a unique hexadecimal string. This hash is permanently published on-chain and mirrored to distributed storage, creating an unalterable record. Following this, states 2 and 3 activate to allocate initial protocol-owned liquidity reserves and lock in early contributor shares, all before any public interaction is permitted. By committing these hashes up front, the developers forfeit their access. The protocol mathematically eliminates the possibility of silent variable edits, hidden mints, or sudden liquidity withdrawals later in the sequence. With the foundation locked, the protocol transitions to the participant entry phases: State 4, Perception, and State 5, Transformation. This is where SAW deploys its primary defense against mempool sniping, the commit and reveal loop. Instead of submitting a standard transaction, this visualization breaks down the exact mathematical payload participants submit. Users generate a Ketchak 256 hash containing their wallet address, allocation amount, and a random nonce. Because hashing is a one-way function, this commitment blinds MEV searchers. The specific order size remains entirely hidden while waiting in the mempool. Once the commitment window closes, the protocol enters State 6, Harmony. Here, participants publish their original plain text data to the network. The smart contract then executes a strict validation check. It hashes the newly revealed plain text on-chain. If that output does not perfectly match the original commitment hash from State 5, the transaction is purged. This isolates adversarial actors. Front-running requires precise knowledge of a target's parameters. By hiding those parameters until execution is locked, bots cannot exploit the order flow. Once all valid participants are revealed, State 7 addresses the core engineering dilemma: how to fairly determine the order of distribution without relying on speed. Native Ethereum virtual machine time functions are unreliable for secure ordering.
Functions like block timestamp or prev_random are calculated by the validator proposing the block, meaning the validator can subtly alter the timing to favor specific transactions. SAW achieves this through a quantum timestamp, a cryptographic consensus derived from multiple independent external clocks. The entropy aggregator pulls data from 4 distinct sources: a future Ethereum block hash, drand randomness, NTP servers, and an external chain anchor. This creates a tamper-evident fingerprint. Manipulating this requires simultaneously compromising all these networks at the exact same moment. Once verified, this aggregated entropy hash is injected directly into the protocol's allocator contract. The contract calculates the final queue by combining the global entropy with each individual participant's wallet address. This generates a purely deterministic numerical list of users. A traditional Gauss war allows users to pay for priority placement. Here, a user's position is dictated strictly by the output of the hash function. By offloading sequence generation to unpredictable, multi-source math, the protocol eradicates the first-come, first-served advantage. With the order mathematically cemented, the protocol moves into execution across states 8 through 10. Standard token distributions process transfers sequentially, requiring a distinct transaction for each user. This leaves the later transfers vulnerable if mempool conditions change midway. SAW operates on an atomic batch execution model. The settlement contract executes all user allocations in a single unified call. Every participant receives their tokens simultaneously within the exact same block. This provides a security failsafe. If any parameter is invalid, or if gas limits are breached, the entire settlement sequence reverts. It either succeeds perfectly for every participant, or it fails entirely. Immediately following distribution, State 9 deploys the protocol's liquidity. It uses the exact time lock hash committed during State 2 to secure the liquidity pool without requiring manual developer input. State 10 then safely unlocks the designated ecosystem treasury for future protocol growth. Atomic settlement ensures that no user is ever left stranded in a partially failed state, shielding the entire participant pool from mid-execution exploits. The process concludes with State 11, purity, which seals the protocol. The contract generates a final state hash. As illustrated by this equation, it binds the entire sequence, all executed allocations, the quantum timestamp, and the multi-source entropy into one permanent fingerprint. This establishes a rigorous audit layer. Because the math is public, any external observer can pull these hashes and perfectly recompute the ordering and allocations to independently verify that the execution was completely fair. Finally, State 12 initiates transcendence. The rigid state machine completes its purpose and hands over control of future emissions and treasury adjustments to decentralized DAO governance. The launch event is over, but it leaves behind a permanent, mathematically provable receipt. Trust in the developers is no longer required. The math provides the verification. Looking forward, EVM networks currently secure transactions using elliptic curve digital signature algorithms, or ECDSA. These signatures are highly vulnerable to the advancing threat of quantum computing. To address this vulnerability, SAO outlines a specific upgrade path. The protocol plans to integrate hybrid signatures, layering classical cryptography with post-quantum safe, lattice-based algorithms like crystals to lithium. The digital asset industry has continually relied on vulnerable timing mechanics, leaving users exposed to speed advantages and obscured execution logic. SAW strips away those vulnerabilities, hiding intent through commit and reveal, deriving order from multi-source entropy, and executing via atomic batch settlements. It provides a mathematically rigorous alternative. True legitimacy in decentralized systems cannot be promised by developers. It must be engineered, proven, and cryptographically sealed.